In this video, I discuss properties of a discrete Fourier transformation. Because quantum Fourier transformation is based upon discrete Fourier transformation, therefore properties of discrete Fourier transformation are also inherited by quantum Fourier transformation. There are several properties of discrete Fourier transformation, but in this video I will discuss only 3 of those properties, because these 3 properties are currently being used in existing quantum algorithms. So let's start. First property of discrete Fourier transformation states that discrete Fourier transformation represents a unitary transformation, which is cool because now we can make quantum circuits of discrete Fourier transformation and implement discrete Fourier transformation on quantum computers. There are different ways to prove this property, but a simple way is to show that the columns of discrete Fourier transformation matrix are orthonormal. It implies that each column is normalized, or its magnitude is equal to 1, and each column is orthogonal from all other columns. So if we have 2 columns of discrete Fourier transformation, say column J and column K, and we take dot product of those columns, then our result of dot product must be either equals to 0 or equals to 1. Our result must be equals to 0 when J is not equals to K. That means column J and column K are different columns, and this shows that columns are orthogonal. Our dot product must be equals to 1 when column J and column K are the same column, and this represents that our columns are normalized. So now let's verify this property, or let's prove this property. So we take ith column of discrete Fourier transformation. The ith column will be equals to 1 over square root of not I but jth column. Jth column will be equals to 1 over square root of n times omega raised to power 0th row times jth column. Second entry of the vector will be omega raised to power first row times jth column. Third entry will be omega raised to power second row times jth column, and the last entry will be omega raised to power n minus 1th row times jth column. We can simplify it. It will be equals to 1 over square root of n, and first entry will be 1, second entry will be omega raised to power j, third entry will be omega raised to power 2j, next entry will be omega raised to power 3j, and the last entry will be omega raised to power n minus 1j. Similarly, we can write kth column of the discrete Fourier transformation matrix. That will be equals to 1 over square root of n, and first entry will be 1, just like previously we have computed those entries. So second entry will be omega raised to power k, third entry will be omega raised to power 2k, next entry will be omega raised to power 3k, and the last entry will be omega raised to power n minus 1k. Now we compute dot product of column J with column K. So our dot product with column J and column K will be equals to that we have to take conjugate of the first column, each entry, and multiply it with the corresponding entry of the second column. So our results will be equals to 1 over n, because when we multiply 1 over square root of n with 1 over square root of n, we get 1 over n summation. Let's say m is equals to 0 to n minus 1, and then first entry will be like omega raised to power m times j conjugate times omega raised to power m times k, and this will be equals to 1 over n summation m is equals to 0 to n minus 1, and it will be equals to omega raised to power, because the sign of the first omega will change, because the iota will change its sign because of the conjugate, so it's going to be m, and we have here k minus j. So this is our dot product. Now let's consider these two cases. Our case 1 is that j is equals to k. That means they are both the same column. In this case, our dot product of jth column with kth column will be equals to 1 over n summation from m is equals to 0 to n minus 1 and omega raised to power 0, because when k and j are same, then this becomes 0, and so the power of omega will be equals to 0. And this will be equals to 1 over n, and now we have here all the ones, because omega raised to power 0 is equals to 1, so we will have here 1 plus n times 1, and this will be equals to n over n is equals to 1, thus showing that each column is normalized, or each column is a unit vector. So we have shown half of the proof. So now we have to show the second case, that columns are orthogonal with each other. That means when j is not equals to k, then their dot product is equals to 0. To that end, we can observe that dot product is basically a geometric series. So let's quickly revise the geometric series. So when we have a plus r square a plus r n minus 1a, then the sum of such a geometric series is equals to a r n minus 1 divided by r minus 1. In this case, our a is equals to 1. So in this case, our a is equals to 1 and our r is equals to w k minus j. So we want to show case number 2, that is when j is not equals to k, that means j and k represents different columns, then their dot product is equals to 0. That means we want to show that 1 over n summation m is equals to 0 to n minus 1 omega m k minus j is equals to 0. So now using the formula of geometric series, we compute that the dot product of jth column and kth column will be equals to omega k minus j times n minus 1 divided by omega k minus j minus 1. Now whenever we have omega n raised to power any multiple of n, let's say fn, then this is always equals to 1. It is because omega represents a modular function, so we can write omega n raised to power fn as omega n raised to power fn mod n. and this will be equals to omega n raised to power 0, and that will be equals to 1. Therefore, this term will be equals to 1 because it has a power which is multiple of n. So we have 1 minus 1 which will be equals to 0. Hence showing that column J and column K, when are not the same column, then their dot product will be equals to 0, proving that they will be orthogonal with each other. The second property, which is widely used by quantum algorithms, is a simplified case of convolution-multiplication property. So the basic idea is that I linearly shift my input vector and then apply a quantum Fourier transformation on that input vector, and my output vector has a phase shift in it. And this is cool. And why this is cool, I will get back to it later on, but let's first explain this property. So I have my quantum Fourier transformation matrix, which is same as the discrete Fourier transformation matrix, and then I apply an input vector to that matrix. So my input vector is alpha 0, alpha 1, alpha 2, and alpha n minus 1, and my output will be equals to beta 0, beta 1, beta 2 to beta n minus 1. Obviously, my input vector is in superposition and my output vector is also in superposition. So if I measure my output vector, then my result is an index of the vector. Let's say my result is index k, and the probability of measuring index k is equals to magnitude square or corresponding amplitude. So my probability is equals to beta k whole square. And now if I linearly shift my input, so my input is linearly shift, let's say by 1. So here my input is linearly shift by 1. So now I have alpha 0 here, alpha 1 here, and at the end I have alpha n minus 1, whereas alpha n minus 2, whereas the last entry is now the first entry. So first entry is become alpha n minus 1. In this case, my output is exactly the same but has a phase to it. So my output will once again will be beta 0, beta 1, beta 2, and last entry of output will be beta n minus 1, but I have a phase with my output entry. So the first entry will be multiplied by omega, second entry will be multiplied by omega square, and the last entry will be multiplied by omega n minus 1. And now if I measure this new input vector, my answer will be random index k, and with probability once again equals to same probability, which is beta k whole square. It is because magnitude of omega or any power of omega is equals to 1. So the magnitude of omega square or magnitude of omega or magnitude of omega let's say cube is equals to 1. Because magnitude of all the powers of omega is equals to 1, and therefore I don't have to write here omega k. I can just ignore it because it's going to be 1 anyway. And this is cool because many times my input vectors have a linear shift in them, and when I want to measure them, I don't want to have linear shift in my measurement. So I can apply quantum Fourier transformation on my input vectors, eliminate the linear shift, and then I measure my input. And we will do this thing when we will be working on period finding algorithm in one of the videos. So can we prove that this is true? Can we prove that the result that we have here is correct? So now let's quickly show that this property is correct. Before linear shift, this is before linear shift, this is after linear shift. So before linear shift, my kth output, which is beta k, is multiplication of this kth row of the matrix with the input vector. So it's going to be equals to alpha 0 plus omega k alpha 1 plus omega 2k times alpha 2 plus, and the last entry is going to be omega n minus 1 k times alpha n minus 1. This was the kth entry of the output before linear shift. So this was kth output element before a linear shift by 1. Now I linear shift my inputs by 1. So linear shift implies that my the alpha m will be equals to alpha m plus 1, because my alpha 0 is going to replace alpha 1, my alpha 1 is going to replace alpha 2, and so on and so forth. So after linear shift by 1, my kth output will be equals to, here I have alpha n minus 1, because it is circular, so the last element will become first element, and then I have omega k, and here I have alpha 0, and then I will have omega 2k times alpha 1, then I have omega 3k times alpha 2, and the last entry will be omega n minus 1 k times alpha n minus 2. So this is our kth entry, kth output after linear shift. So this is our kth output after linear shift. And now what we have to show is that this output is same as the output before linear shift, but only has a phase attached to it. So what we have to show is that this output is equals to omega raised to power k times previous output, which was beta k. And this is easy to show, because when we multiply our previous output with omega raised to power k, we get this output, because when we multiply alpha 0 with omega raised to power k, then this is same as my output after the linear shift. Similarly, if I multiply second entry with omega k, it will get omega 2k times alpha 1, which is same as this entry of the output after the linear shift. Similarly, when I multiply my last entry with omega k, it will be equals to omega raised to power nk times alpha n minus 1, and omega raised to power nk is equals to omega raised to power 0, because nk mod n is equals to 0. So nk mod n is equals to 0. Therefore we have here omega raised to power 0, and this is basically my first entry, because omega raised to power 0 is 1, so my first entry is going to be alpha n minus 1. So the key is that my output remains the same after linear shift by 1, only I have a phase attached to that output, and phase is ignored when I measure that output. Similarly, if I do my linear shift instead of 1 by any other digit by m, then once again I have a different phase attached to my output, but my output will remain the same. So now let's do the third property. Last property, which is used by quantum algorithms, is period and wavelength relationship. So assume that we have a function f, and function f takes n bits as input, and it produces n bits outputs. And we apply a quantum Fourier transformation on our function f, which is discrete Fourier transformation, and thus getting transform function f hat x. And if our function f is periodic and has a period of r, so if it has a period of r, then the transform function will have a period of n over r, capital N over r, where capital N is equals to 2 raised to power n over r. So if I take quantum Fourier transformation matrix, which is same as discrete Fourier transformation matrix, and I apply that on the range of my function f, the function which was periodic, so the range is going to be alpha 0, alpha 1 to alpha r minus 1, and then it will repeat itself because of periodicity. So once again I will have alpha 0, alpha 1 and so on. Then my transform output, it will be beta 0, beta 1, and output will also be periodic, but its period will be capital N over r, and then output will repeat itself from beta 0, beta 1 and so on. Proof of this property is a bit more involved, so I'm saving it for the future videos. That is it for this video. See you next time.